In this video, we'll understand the basics of Retrieval-Augmented Generation, or RAG, in a simple step-by-step way. We'll see why normal LLMs can give outdated or hallucinated answers, and how RAG improves reliability by retrieving relevant information before generating a response. Along the way, we'll also cover chunking, embeddings, vector databases, cosine similarity, and prompt design. And yes, there will be quizzes in between, so you can quickly check your understanding. RAG stands for Retrieval-Augmented Generation. The idea is quite practical. Instead of asking a language model to answer only from what it remembers from training, we first retrieve relevant information from an external knowledge source, and then ask the model to generate the answer using that context. So RAG is basically a two-part system working together: fetch useful information, then write a good response. This makes answers more grounded and more useful, especially when the question depends on specific facts. A normal LLM may sound confident even when it is wrong. For example, if you ask which planet has the most moons, an older model might say Jupiter based on old data. But if a RAG system retrieves fresh information from a trusted source like NASA, it can correct that answer to Saturn with the updated count. This is the real value of RAG. It helps the model move from confident guessing to evidence-backed answering. The basic structure of RAG has three stages. First comes indexing, where documents are processed and prepared for search. Second is retrieval, where the system finds the most relevant pieces for the user's query. Third is generation, where the LLM uses those retrieved pieces as context and creates the final answer. If you remember just one structure from this lesson, remember this flow: index, retrieve, generate. Indexing is the preparation step. Raw documents are usually too large to search efficiently as one big block, so they are broken into smaller parts called chunks or splits. Each chunk should ideally contain a meaningful piece of information. This helps the system search at a finer level, instead of dragging in entire documents when only one paragraph is relevant. Good indexing lays the foundation for good retrieval. Now that we've covered RAG foundations, let's test what we've learned so far.
Here's quiz number 1. See if you can get it right.
Question 1. What does RAG combine? The correct answer is retrieval and generation. RAG combines information retrieval with text generation, so the model can answer using relevant external context. Question 2. Why is RAG useful for LLMs? The correct answer is it helps with outdated or inaccurate answers. RAG improves factual grounding by retrieving up-to-date and relevant information before generation. Question 3. Which is the correct high-level array flow? The correct answer is index, retrieve, generate. The article explains the three core components of RAG as indexing, retrieval, and generation. Chunking is not just a technical step, it directly affects answer quality. If chunks are too large, retrieval may bring in noisy or unrelated content. If chunks are too small, important context may get lost. The goal is to create manageable sections that preserve meaning while making search efficient. In practice, chunking helps the system focus on the exact section that answers the question, rather than searching blindly through huge documents. Once chunks are created, each chunk is converted into an embedding. An embedding is basically a numerical representation of the text, designed so that semantically similar pieces stay closer in vector space. These embeddings are then stored in a vector database. This is what makes fast semantic search possible. Instead of matching only exact words, the system can now search by meaning. When a user asks a question, the query is also turned into an embedding. Then the vector database compares that query vector with stored chunk vectors and returns the closest matches. This is often done using methods like KNN, HNSW, or tools like FAISS for efficient large-scale search. The important point is simple: retrieval is based on semantic similarity, not just keyword overlap. A common way to compare embeddings is cosine similarity. It measures the angle between two vectors. If the angle is small, the vectors point in a similar direction, which usually means the meanings are similar. This is useful because it cares more about direction than magnitude. So even if vectors have different lengths, the system can still compare their semantic alignment properly. In RAG, this helps identify which chunks are most relevant to the question. Now that we've covered retrieval pipeline, let's test what we've learned so far.
Here's quiz number 2. See if you can get it right.
Question 1. What is chunking in RAG? The correct answer is splitting documents into smaller sections. Chunking means dividing large documents into smaller manageable pieces for indexing and retrieval. Question 2. What is stored in a vector database? The correct answer is numerical embeddings of chunks. After chunking, each chunk is converted into an embedding and stored for similarity-based retrieval. Question 3. What does cosine similarity measure? The correct answer is the angle-based similarity between vectors. Cosine similarity compares the direction of vectors, making it useful for semantic similarity search. After retrieval, the final step is to pass the retrieved context to the LLM in a well-designed prompt. A strong RAG prompt usually includes the context, the user's question, and clear instructions on how the model should answer. This matters a lot. Even with good retrieval, a weak prompt can lead to vague or off-topic output. A standard template helps the model consistently use the retrieved evidence instead of ignoring it. So overall, RAG helps solve several common LLM problems. It reduces hallucinations by grounding answers in retrieved sources. It handles dynamic knowledge better because it can access newer information. It also performs better on niche or specialized topics when connected to domain-specific data. In short, RAG does not replace the LLM. It upgrades the LLM by giving it the right context at the right time. Now that we've covered prompt and benefits, let's test what we've learned so far.
Here's quiz number 3. See if you can get it right.
Question 1. A good RAG prompt usually includes which two key elements? The correct answer is context and question. The article highlights that effective RAG prompts combine retrieved context with the user's question. Question 2. How does RAG help with rare or niche topics? The correct answer is, by using specialized databases or sources, RAG can retrieve information from domain-specific sources, which helps on uncommon topics. Question 3. What is one major benefit of grounding answers with retrieved context? The correct answer is improved factual accuracy. Retrieved context gives the model evidence to work with, which improves factual grounding and reliability. That's the basic implementation idea behind RAG. If you understood the flow from chunking to embeddings to retrieval to prompting, you already have a strong foundation. From here, you can move into practical tools like LangChain, FAISS, and full end-to-end RAG pipelines. Nice work and keep learning.